This is Honors Algebra 2 Pre-Calculus. We're doing 10.8 in Pre-Calc, which is graphing in polar. So this entire video is going to talk about symmetry. I'm using the abbreviation WRT to mean with respect to. Sorry, I missed a quote here. That's a pretty common math abbreviation. So WRT means with respect to. And you'll see it when we get to Calc 2 when we talk about deriving with respect to x or with respect to t. But so here we're going to talk about three kinds of symmetry. So I know it's a lot, so we're just going to kind of do one at a time. Okay, so first kind of symmetry. With the symmetry with respect to theta equals pi over 2. So theta equals pi over 2 is basically the positive y-axis, right? It's right here. Okay, so if you're symmetric to that, then if the point r comma theta is on a graph, so is the point negative r comma negative theta. Let me show you why that's the easiest way to write this coordinate. Negative theta, so if this is theta, negative theta means rotate clockwise the same amount. That would make this spot negative theta. And then if instead of walking forward on negative theta, I walked backwards r units, you'll see how I end up in this spot here. So negative r comma negative theta. So when we talk about testing for that kind of symmetry to see if we're symmetric about the line theta equals pi over 2, the easy way to test that is to plug in this negative r comma negative theta into whatever original equation you're given. If you simplify that and it simplifies to exactly the original equation that you were given, then you're looking at a graph that's symmetric to that essentially positive y-axis, but it's actually the line where theta is equal to pi over 2. So we're going to do examples of symmetry in a little bit, but that's how you would test that. I never have bothered to memorize these. I bothered to memorize symmetry for functions because functions in terms of x and y in Cartesian coordinates, very, very useful to know basic symmetry stuff about whether something is an even or an odd function. But honestly, with regards to polar, unless you plan on picking a career where you're graphing polar by hand a lot, which would be an unusual choice, I think, there's not a whole lot of reason to memorize the symmetry here. It's good to understand how it works. It's good to see the logic of why I'm telling you what I'm telling you, and to be able to apply it if you had these rules in front of you. But in terms of memorization, I don't actually think that it's something that you have to have memorized. And you know, we learn a lot of stuff in this class and in all of our other classes and just in the world at large. And it's impossible to memorize everything that you learn, so you start to have to make those choices and decide what stuff is better to memorize and what stuff is just better to be able to apply when you're handed the information. So I would argue this is an application over memorization. So let's go to the second type of symmetry in the middle of the board here. So with respect to the polar axis, now the polar axis is essentially the positive x-axis, right? It's the line where theta is equal to 0, right? So if something's symmetric about that axis, then if I have the point r comma theta here, then this point would be r comma negative theta. Because we already saw in the last type of symmetry that the way I get negative theta is just by rotating the opposite direction the same amount. And then I would just go r units. So again, the test is the same, except instead I'm plugging in r comma negative theta. And if I plug those in, and you'll see, actually, I probably erase this, but on this page in your book, which is page 757, they do give you a couple options for plugging in that are slightly more complicated. They're also fine. I chose the one that is slightly easier. I chose the one that basically I would use if I were you. The reason I chose these is because they don't require simplification to the magnitude of like using the cosine of u plus v formula or something, which I think a lot of us don't want to have to do from memory. So I think this is the easier option. So again, if you want to test for symmetry with respect to the polar axis, you would plug in r comma negative theta and simplify the expression. If that expression simplifies to the same original expression you had when you were using just regular r and theta, then you're symmetric to the polar axis. The third kind of symmetry, with regard to the pole, right? So the pole is essentially the same spot as the origin, okay? So symmetry with respect to the pole, well, this point is r comma theta. This point is at the same angle, but just walking backwards. So this is going to be negative r comma theta. Again, if you want to test this, you plug that into an original function. So you plug negative r comma theta in, and if it simplifies to the original, then you have something symmetric to the pole. So I'm actually going to erase the original one because I want to talk about example 1 that we just did, because example 1 exhibits the second kind of symmetry. So if we just go back for a sec to example 1, so we're going to review example 1, which was r equals 3 cosine of theta, right? And we remember that the graph turned out to be like a circle like this, right? So what I want you to notice is that that graph is absolutely symmetric with respect to theta equals 0, or the polar axis, but it is not symmetric with respect to theta equals pi over 2, and it is not symmetric with respect to the pole. So it's going to demonstrate this type of symmetry, the symmetry with respect to the polar axis, and I'm going to show you how that works. So if we were to test right? If we were to test for theta equals pi over 2 symmetry, which is the version I called A, right, then we would be plugging in negative r negative theta, right? And we would try and get this same expression back. Now that's going to fail because I can see with my eyes that that's going to fail. So if I tried negative r equals 3 cosine of negative theta, well, I know that cosine is an even function. So when you plug a negative into an even function, it comes out positive. So I'm going to get negative r equals 3 cosine theta, which is not the original function. I end up with an extra negative that I'm not supposed to have. So it does not have symmetry with respect to theta equals pi over 2. If I test it with respect to this, the one that I know should work, right? If I test it with respect to the polar axis, right? With respect to the polar axis, I would use the point r comma negative theta. And again, I don't need you to memorize which points you're using to test which thing. You just need to be able to apply them if they're handed to you, right? So if I try plugging this in, I get r equals 3 cosine of negative theta. But as we just saw previously, r equals 3 cosine negative theta, because cosine's an even function, is just the same as 3 cosine theta. Well, that's my original. So yes, I have symmetry with respect to the polar axis, which you could see from the graph we did in example 1. Now, if I tested it one more time, right, let's test it with respect to the pole, which again, we know is going to fail, right? But if I test this with respect to the pole, right, the thing I want to plug in to test with respect to the pole is a negative r comma theta, right? So I would plug in negative r equals 3 cosine of regular theta. Well, there's no way to simplify that at all. That's just a no, right? There's nothing I can do about the... So unsurprisingly, we get that the graph that we did in example 1, which we could see with our eyeballs was symmetric only to the polar axis, is in fact symmetric to the polar axis. There are some graphs that are symmetric to none of these, and that's okay. Just like we see in graphs in regular functions, we can talk about even, odd, and neither. There are some graphs that are neither. They are neither symmetric to the y-axis, nor the x-axis, nor to the origin, right? There are things that are not symmetric at all. So in this case, we ended up with a graph that was symmetric in one direction. Now, one of the reasons it can be useful to know stuff about symmetry is that if you know something is symmetric to the polar axis, like the one we did here, sometimes you only have to graph the top half, because if you know that this top half, the first half you graph, is identical to the bottom half, then you graph the top half, and then you just copy your own work on the bottom, which is a lot faster. So that's one of the reasons that the textbook makes a point about symmetry, is because if you're graphing by hand, symmetry, although it seems time-consuming at the beginning, could save you a lot of time because you can only end up graphing half of the graph and then just copying your own work. That's kind of the idea.